Hi everyone, I'm Marco Costa and I will talk about asymmetric accidental composite dark matter models. Work has been done in collaboration with my colleagues at Scuola Normale, Salvatore Bottaro and Oleg Popov. First I will review what accidental composite dark matter models are, ACDM in short. I will talk about the conditions needed to asymmetrize them, discuss a simple implementation for the asymmetry generation mechanism, and then conclude. So, what are ACDM models? They are dark matter models in which you have a confining dark color group based, for example, on SUN. The elementary degrees of freedom are dark quarks, which are QCD-like fermions in the fundamental of dark color and with a non-trivial standard model charge. Dark matter is the lightest stable dark baryon, and in the light dark quark limit, the abundance is simply set by one parameter, which is the mass of the dark baryon, and the relic abundance is reproduced by taking the dark baryon in the 100 TeV range. So, if one wants to classify these models, some assumption must be done, as was done in the original ACDM work by Antipin et al. They considered dark quarks with standard model representation that came from SU5 grand unification fragments, as shown in the table. Then they asked for the dark sector to have a neutral or at most weakly interacting dark matter dark baryon to avoid phenomenological bounds, and then they also asked the bound state to be accidentally stable, thanks, for example, in this kind of SUN based models, thanks to a U1 which corresponds to the dark baryon number. Here is the list of the models allowed by the requests, and now I want to introduce how we can make such model asymmetric. So, what do we mean by asymmetric dark matter models? We mean models in which there are more particles than antiparticles. These lead to a different phenomenology. For example, there are different bounds coming from indirect detection, or coming also from the fact that now the dark matter particle can form long-lived bound states. Also, in the asymmetric scenario, there is a different relation between the abundance and the mass of the dark matter candidate. And possibly, in asymmetric dark matter models, there is the possibility to link the visible asymmetry to the dark sector asymmetry. This last point has not been explored, but it's something that we wish to work on in the future. Now, given with this definition of asymmetric dark matter models, how can we make them asymmetric? One must meet the so-called Sakharov conditions. Indeed, you must break the U1 of the dark baryon candidate if you want to generate an asymmetry for it, and already this must be done in a careful way, because in ACDM models, this U1 is the symmetry that stabilizes the dark matter candidate, and if you break it, it's not obvious that it's still stable. Then you need some CP violation, which is equivalent to ask for the existence of complex couplings and physical CP violating phases. And as a final requirement, you need to specify some out of equilibrium process. Already, by looking at point 1 and 2, it's clear that in QCD-like theory are not enough to generate the asymmetry, because they do not have any U1 breaking interaction, and also they do not have any CP violating term if the theta angle is set to 0. So, what we must do is to consider a new scale, lambda CPV, at which some new fields and interaction appear. These are responsible for the breaking of the U1 dark baryon and also for the generation of the asymmetry of dark baryons. At low energy, the U1 dark baryon must become an accidental symmetry in the infrared. In this limit, the asymmetry generated at lambda CPV will be conserved approximately. And then, this model at confinement scale essentially reduces to the original ACDM models, only with an initial asymmetry. Then, at lambda DC, so you will have your dark quark confining, the dark pion will decay in the standard model, and the asymmetry will be stored in the lightest stable dark baryon. Now, we also want to annihilate the symmetric component if we want the dark sector to be asymmetric. What does it mean? This is the picture of the dark sector after confinement. You have a symmetric component, which is common to dark baryon and anti-dark baryon, plus the asymmetric non-thermal component. If the annihilation cross-section between dark baryon and anti-dark baryon is large enough, then you can completely eliminate this symmetric component. In this limit, the radical abundance will be proportional to the mass of the dark baryon times the asymmetry coefficient, asymmetry yield eta. Now, how large must the cross-section be? Well, here we plot on the right the dark matter mass, which in turn is determines the cross-section, and on the y-axis the ratio between the number of antiparticle and dark matter dark baryon particles. As can be seen, this ratio can be made smaller than 1% by requiring the dark baryon mass to be lighter than 70 TeV, and the ratio can be made even smaller by taking the dark baryon even lighter. So, with respect to the symmetric case, we have lighter dark matter. Now, if we want to compute the asymmetry yield eta, we must specify a model, and we do so by considering this simplified model in which we have the dark quark n charged in the fundamental of SU3 dark color in standard model singlet, and the scalar phi, which is in the symmetric of SU3 dark color. This Lagrangian admits a Yukawa interaction between phi and n and a trilinear phi cube term. Now, under this assignment of dark baryon number, the Yukawa preserves it while phi cube violates it. However, the dark baryon, which is n cube, is still accidentally stable thanks to a residual Z2 under which only n is charged. Therefore, the dark matter, while U1 is broken, is still stable. Now, what is the process responsible for the asymmetry generation? Well, here we consider a modified benchmark model in which we consider two flavors of phi heavy, phi h, and phi light, phi l. Phi h can decay into two channels with different dark baryon numbers, phi going in n bar and phi going into phi light star and n. The latter three-body decay channel violates the dark baryon number by 6 units. Now, if phi h and its conjugate phi h dagger distributes themselves differently in these two channels, we can generate an asymmetry. This is done by having this epsilon parameter to be non-zero. Now, in the so-called weak washout regime, which is realized if m phi is larger than 10 to the 15 GeV, we can neglect inverse decay process, which usually destroy the generated asymmetry. In this regime, the asymmetry yield is proportional to the epsilon parameters divided by the number of relativistic degrees of freedom at the time of decay, G star, and is easily computable. The CP violation, instead, in the two-flavor model, is allowed because there are three physical phases, and the CP violating processes come from the interference between the three-body decay, three-level decay, with the one-loop correction, which comes in the form of bubble diagrams and box diagrams. Now, in these models, we can compute the epsilon parameters, and therefore eta, as a function of the ratio m heavy divided by m light, which is called alpha. Here, it's shown on the left, we switched off two of the three phases while keeping only one, and we've plotted epsilon as a function of alpha with different choice of parameters. Here, R is the ratio between the two Yukawas in the models, and this can be shown by taking the Yukawa around 0.1. We can reproduce the needed epsilon for dark matter models in the TeV range, which is required for the annihilation of the symmetric component and collider bounds. On the right, we have plotted the results for epsilon by switching on all the three phases and by sampling randomly all the couplings between 0.1 and n1. And as can be seen, the asymmetry can be generated in TeV range. Now, we need to implement this benchmark model in the full ACDM models, but this is done easily because if your ACDM model has n, you can copy what we have done before. There might be some additional couplings, but nothing changes drastically. Instead, if there isn't n, there is the SU2F triplet V. And again, you can copy what we have done before by simply replacing n with V. Instead, if you have colored ACDM models, you need to replace actually the representation of phi, and instead of having phi cube, you need phi cube h star, having a 4-body decay process rather than the 3-body decay one. But eventually, also in this case, things go as usual. To conclude, we have built a symmetric extension of ACDM models. The symmetric component is annihilated without adding any extra interactions. The mechanism generates the correct asymmetry, and the dark matter candidate is stable while U1 dark baryon is broken. And the mechanism has been implemented in all the original models. What's next? We would like to link the standard model asymmetry to the dark sector asymmetry and possibly study other dynamics. Thanks for the attention.